4:51 in the morning on Saturday, the 25th of July, 2026, the ground beneath the central North Island of New Zealand let go. GeoNet, the country's official geological hazard monitor, placed the rupture 5 kilometers south of the town of Taumarunui at a depth of just 9 kilometers. The magnitude came in at 5.9. Within 6 hours, GeoNet's seismographs had located 78 aftershocks trailing away from that point, the strongest of them a magnitude 3. 7 that struck about 30 minutes after the main shock. More than 23,000 people felt reports with GeoNet in the hours that followed, from Auckland in the north to the top of the South Island, a spread of feeling that tells you almost everything about how this particular earthquake behaved. This was not a quake that stayed quiet in one valley. It reached out across an entire country. Numbers like these are easy to skim past, so it is worth sitting with them for a second before going further, because every one of them is doing real work in explaining what happened that morning. A depth of 9 kilometers is shallow by any standard. A magnitude of 5. 9 is strong, but not enormous, the kind of earthquake that shows up somewhere on Earth several times a month. Put those two numbers together, though, and you get something disproportionate to its size. A rupture close enough to the surface that almost all of its energy arrived at ground level with very little of the planet left to absorb it on the way up. GeoNet's own shaking model assigned a maximum intensity of MMI 6. 5, close to the epicenter, a level at which furniture slides across floors, objects are thrown from shelves, and buildings can pick up slight non-structural damage, cracked plaster, fallen chimneys, that sort of thing. That is a serious jolt for anyone standing on top of it, even if the magnitude itself would not have made international headlines on its own. The practical consequences on the ground were immediate, if not catastrophic. State Highway 43, the road that links Wangamomona to Taumarunui through some of the roughest country in the North Island, closed after slips came down onto the carriageway. State Highway 3 through the Iwakino Gorge was also shut by a slip. It is worth being honest about the cause here, rather than pinning everything on the earthquake. The district had already been soaked by heavy overnight rain, and wet hillsides fail more easily than dry ones, regardless of what is shaking them. The quake and the rain share the blame for those closures, and untangling exactly how much each contributed is not really possible from the outside. What is clear is that no deaths and no serious structural damage were reported, which, for a magnitude approaching 6 on shallow ground under a populated district, counts as a fortunate outcome rather than an expected one. Before going any further into the geology, it is worth addressing the question that will have crossed a lot of minds the moment this quake made the news, because Mount Ruapehu sits only about 55 kilometers to the southeast of the epicenter, close enough that a shallow shake near a major volcano naturally raises the word eruption in people's heads. The answer, according to GeoNet, is no. This was a tectonic earthquake, rock breaking along a fault line under mechanical stress, not magma forcing its way toward the surface. As of Saturday afternoon, GeoNet's volcanic alert levels sat exactly where they had been before the quake. Ruapehu remained at level 1, which denotes minor volcanic unrest, a status it had held for some time already and continued to hold afterward without any change attributable to the earthquake. Tongariro, Ngauruhoe, and Taupō all remained at level 0, the baseline dormant setting. Nothing about Saturday's rupture nudged any of those needles. That does not mean the volcanoes are irrelevant to the story, though, because the connection between this earthquake and the region's volcanic geography is real. It is just indirect rather than causal. Taumarunui sits right at the western edge of the Taupō Volcanic Zone, a long belt of stretched, thinned, and heated crust that runs from Ruapehu in the south up to White Island out in the Bay of Plenty. This zone exists because the Pacific Plate is sliding, or subducting, beneath the Australian Plate along the eastern side of the North Island, and the mechanics of that subduction pull the crust above it apart, thinning it and letting heat and eventually magma rise closer to the surface. That stretching is what gives the central North Island its chain of volcanoes and its geothermal fields. But the same regional tension that thins the crust in the middle of the zone and lets magma through also puts stress on the rock at the zone's edges, and when that stress builds past what the rock can hold, it breaks. Saturday's earthquake happened at exactly that kind of edge. The volcanoes and the earthquake are, in a sense, two different symptoms of the same underlying process, a piece of continental crust being pulled apart by the plate boundary sitting beneath it. There is a genuinely interesting side effect of that same volcanic geology that shaped how far Saturday's earthquake actually traveled, and it is one of the more counterintuitive findings GeoNet noted in its response. You might expect shaking to radiate outward from an epicenter in a rough circle, weakening steadily with distance in every direction. That is not quite what happened here. GeoNet observed that the seismic waves lost energy unusually quickly as they crossed the Taupō Volcanic Zone itself, which lies to the east of Taumarunui. The hot, fractured, geothermally active rock under that volcanic plateau essentially absorbs and dampens seismic energy passing through it, acting almost like a shock absorber built into the landscape. As a result, the east coast of the North Island, including places like Gisborne, was spared the intensity of wake-up call that towns to the north and south experienced. The shaking, in other words, did not spread evenly. It found the paths of least resistance through cooler, harder, more efficient rock to the north and south, while the geothermally softened crust to the east quietly ate a chunk of the energy that tried to pass through it. That is a detail that would be easy to miss if you only looked at a magnitude number, and it is a good reminder that how far and how hard an earthquake is felt depends as much on the geology it travels through as it does on the size of the rupture itself. So, what actually broke? GeoNet's science response team described this as normal faulting, which is a specific and meaningful term in earthquake seismology, not just a generic label for regular earthquake. To understand normal faulting, picture a slab of crust under tension, being stretched apart rather than squeezed together or sheared sideways. Eventually, the rock fractures along a sloped plane, and the block on one side of that fracture slides downward relative to the block on the other side, pulled by gravity now that the tension has found a release point. That is fundamentally different from the earthquakes most people picture when they think of a major seismic event, the kind produced by two plates grinding past each other sideways, like the San Andreas Fault in California, or the kind produced by one plate being thrust up and over another, like the great subduction earthquakes that strike Japan and Chile. Normal faulting happens where the crust is being pulled apart, and GeoNet's official statement was direct about the cause. This earthquake was due to normal faulting, extension of the Earth, in the upper crust of the Australian plate, in an area at the edge of the Taupō Volcanic Zone, where the crust is stretching thinner because of the subduction of the Pacific plate below and the processes that subduction sets in motion. That is about as clean an explanation as seismology offers for why a particular patch of ground gave way on a particular morning. The shallow depth of this rupture is what genuinely sets it apart from the recent seismic history of this exact district, and it is worth spending some time on why depth matters so much, because it is easy to treat magnitude as the only number that counts, and depth as an afterthought. Most of the larger earthquakes recorded under the central King Country region, the area Taumarunui sits within, happen far below the surface, down inside the slab of Pacific plate that has been sinking beneath the North Island for millions of years. The clearest comparison is a magnitude 6. 2 earthquake that struck beneath almost the same part of the King Country back in October of 2018, roughly 20 kilometers southwest of Saturday's epicenter. That 2018 quake, despite being noticeably larger in magnitude, ruptured 207 kilometers down. At that kind of depth, the energy of an earthquake has an enormous amount of rock to travel through before it reaches anyone standing on the surface, and it spreads out and softens along the way, arriving as a broad, gentle roll rather than a sharp jolt. Saturday's earthquake did the opposite. Rupturing just 9 kilometers down meant its energy had almost nowhere to go but straight up, delivered directly into the towns, sitting above it with none of the natural softening that a deep quake provides. That is the real reason the shaking near Taumarunui registered as severe despite a magnitude that, on paper, was smaller than the 2018 event. It also explains why residents have been feeling so many of the aftershocks so distinctly. Shallow aftershocks punch well above their nominal magnitude in terms of how strongly people actually experience them. It is worth pausing on one small housekeeping detail here, because attentive readers who go looking for confirmation of this event's size may notice a discrepancy and wonder if something has been revised or walked back. The United States Geological Survey lists this same earthquake at a moment magnitude of 5. 7. While GeoNet's preferred figure, the one used throughout this account, is 5. 9. Both agencies are looking at the same physical event. The difference comes down to methodology. Different seismic networks, different station coverage, and different processing techniques for calculating moment magnitude can produce figures that vary by 1/10 or 2 of a unit for the same earthquake, especially in the hours and days immediately following an event before all the data has been fully reconciled. This is a difference of measurement method, not a downgrade or a correction of the event itself. And GeoNet's number is the one adopted here because GeoNet operates the dense seismic network actually covering New Zealand and is the authoritative source for earthquakes within the country. Now, to the question that will matter most to anyone trying to understand the risk this event represents going forward: which fault actually ruptured? And the honest answer, as unsatisfying as it may be, is that nobody knows yet, and there is a real chance nobody ever will name it with certainty. GeoNet's official response does not attribute Saturday's earthquake to any previously known geological structure, and New Zealand's active faults database shows no mapped active fault trace running through the epicenter. This is not a gap in GeoNet's competence. It reflects something true about the King Country as a region. Its tectonics are comparatively quiet, and its fault network is sparsely mapped compared with the areas sitting directly on New Zealand's plate boundary, places like the Alpine Fault down the spine of the South Island or the Wellington Fault running beneath the capital, both of which have been studied intensively for decades precisely because the hazard they pose is so well understood. The King Country has never demanded that level of scrutiny before, because until Saturday, it had never produced an earthquake at this magnitude and this shallowness within living instrumental memory. That said, there are known structures nearby that give geologists somewhere to start looking. To the southeast of Saturday's epicenter, GNS Science has previously mapped the Ruapehu Fault, a north to south, striking normal fault complex that forms the western boundary of what is called the Ruapehu Graben, essentially a long block of crust that has dropped down relative to the terrain around it, consistent with the same regional stretching already described. The northernmost surface trace of that fault system sits near the Ruapehu Spiral, a famous stretch of railway engineering, roughly 30 kilometers from where Saturday's earthquake struck, close to where it meets another mapped structure called the National Park Fault. 30 kilometers is not nothing, but it is close enough that these mapped faults represent the best existing context for understanding the kind of fault geometry active in this part of the island, even if neither one turns out to be the actual structure that slipped on Saturday. More technical data comes from something called a moment tensor solution, produced by the United States Geological Survey, which is essentially a mathematical analysis of the pattern of seismic radiation the earthquake sent outward in all directions. This kind of analysis can reveal the general style and orientation of the rupture even when nobody has mapped the actual fault plane on the ground. In this case, the moment tensor confirms what GeoNet had already stated in plainer language. The crust failed in extension, being pulled apart on a roughly north to south axis, with a genuine sideways or lateral component to the slip as well, meaning this was not a perfectly clean, textbook normal fault rupture, but one with some oblique motion mixed in. The physics of that radiation pattern, though, is mathematically ambiguous in a specific and important way. It allows for two equally valid fault orientations that could have produced the same signal, one striking roughly east to west, and one striking roughly northeast to southwest. The data on its own cannot distinguish which of those two planes is the one that actually ruptured, because moment tensor solutions inherently produce this kind of two-plane ambiguity. There's the fault that broke, and its geometric mirror image and seismic waves radiating outward look the same either way. This is where the pattern of aftershocks becomes useful, even if it cannot fully settle the question. Mapping the first 6 hours of located aftershocks around the main shock shows the cluster spreading away from the epicenter toward the southwest, rather than fanning out evenly in a circle or trailing off to the east or north. If that southwest trending pattern holds up as more aftershocks are located and refined over the coming days and weeks, it would tend to favor the northeast to southwest striking plane as the one that actually slipped, on the general seismological logic that aftershocks tend to cluster along and around the fault surface that ruptured, illuminating its geometry indirectly even when the fault itself has never been surveyed or named. But this needs to be stated carefully. A map pattern like this is suggestive, not conclusive. Aftershock locations from the first few hours after a main shock are inherently less precise than the locations that come later, once seismologists have had time to refine depth estimates and cross-check readings from multiple stations. It will likely take weeks of precisely relocated aftershock depths, essentially building a three-dimensional picture of exactly where the ongoing rupture activity is occurring, before scientists can say with real confidence which of the two candidate planes actually broke, or whether some more complex geometry combining elements of both turns out to be closer to the truth. None of this uncertainty is unusual or alarming in itself, and there is real historical precedent within New Zealand for a fault rupturing with no prior name, no prior map trace, and no advance warning that it existed at all. The clearest example is the Greendale Fault, which produced the magnitude 7, Forcent Darfield earthquake back in 2010, the quake that kicked off the Canterbury earthquake sequence and set the stage for the far more destructive Christchurch earthquake that followed in February of 2011. Before September 2010, the Greendale Fault was entirely unknown to science. It had left no visible trace on the surface of the Canterbury Plains, no hint in the geological record that anyone had picked up on, and then it tore across farmland in a matter of seconds and became one of the most closely studied fault ruptures in the country's history. The broader lesson from that event, and it applies directly here, is that a great deal of New Zealand's accumulated tectonic strain is carried on faults that are either buried under thick sediment, moving too slowly to leave an obvious surface signature, or simply sitting in parts of the country that have never experienced a large enough earthquake in recorded history to reveal their presence. An earthquake on a fault nobody had mapped is, in the New Zealand context, closer to normal than exceptional. There is one more thread of context worth including here, flagged explicitly as background, rather than a direct explanation for Saturday's event, because it would be misleading to present it as settled fact. At the southern end of the Taupō Rift, near the town of Ohakune, geologists have identified a separate set of east to west striking normal faults, active in a zone where the rift itself appears to be dying out or transitioning into something else geologically. Separately, research led by Victoria University's Tim Stern has spent years studying something called the Taranaki Ruapehu line, a deep crustal boundary that crosses the North Island at roughly this latitude. But the earthquakes historically associated with that structure occur much deeper than Saturday's rupture, generally in the range of 25 to 35 kilometers down, nearly 3 to 4 times the depth of the 9-kilometer rupture recorded on Saturday. So while these features exist in the general neighborhood and describe real tectonic complexity in this part of the island, neither one lines up cleanly enough with Saturday's shallow event to be called its cause. Until GNS Science publishes a fuller analysis, possibly incorporating weeks of refined aftershock data, the honest scientific position remains that this was a rupture on a fault in the upper crust that has not yet been identified or named. Turning to how this earthquake sits in the historical record for the immediate area, rather than the region more broadly, the picture becomes clearer and rather more striking. Searching the GeoNet earthquake catalog for shallow events, defined here as 40 kilometers deep or less within roughly 35 kilometers of Taumarunui, going all the way back to 1900, turns up a short list of the largest such quakes on record. In February of 1957, a magnitude 4. 9 struck at 5 kilometers depth. In April of 1995, a magnitude 4. 8 at the same 5-kilometer depth. In September of 1997, a magnitude 4. 6, again at 5 kilometers. Then a gap of over 2 decades before September of 2020, when a magnitude 5. 2 struck, though notably deeper, at 23 kilometers. And then Saturday, the 25th of July, 2026, magnitude 5. 9 at 9 kilometers. Laid out against each other like that, the pattern is unambiguous. Saturday's earthquake is, by a clear margin, the strongest shallow earthquake ever recorded in the immediate Taumarunui area across the entire modern instrumental record, which, for practical purposes, stretches back through most of the 20th century. It is worth being careful about what that catalog can and cannot tell us, because the honest caveats matter as much as the headline finding. The record thins out the further back in time you go. Seismic instrumentation in New Zealand in the 1920s, 1930s, and even the 1940s was far sparser than it is today, and it is entirely possible that smaller earthquakes in this specific area went completely unrecorded in those early decades, simply because there was no instrument close enough to detect them. But an earthquake of Saturday's size and shallowness would almost certainly have registered on the seismic networks that existed from the 1940s onward, once New Zealand's instrumental coverage had matured enough to reliably catch events of this magnitude anywhere in the country. So while it is possible, even likely, that some earthquakes from the earliest decades of the 20th century are simply missing from this list, it is very unlikely that an event as large and as shallow as Saturday's would have slipped through undetected for the past 80 or so years. That combination of facts makes this a genuinely rare earthquake for this specific town. Not an exaggeration built on a thin or unreliable historical record, but a real outlier grounded in data that becomes increasingly reliable across almost the entire period being compared. Looking forward from here, the immediate scientific and public safety picture rests on 2 separate tracks. The first is the ongoing aftershock sequence itself. GeoNet expects aftershocks to continue in the coming days, and because the main shock was so shallow, those aftershocks are being felt far more widely and far more distinctly than aftershocks of similar magnitude would be if they were occurring at greater depth. The same physical relationship between shallow depth and felt intensity that made the main shock itself such a rude awakening. The general pattern for aftershock sequences, well established in seismology globally and not specific to this event, is that both the frequency and the average size of aftershocks decrease over time following the main shock, though not smoothly or predictably. Individual aftershocks larger than expected can and do occur. GeoNet's official response carries the standard caveat attached to essentially every significant earthquake anywhere in the world. There remains a possibility, not a prediction, simply an acknowledged possibility, of another earthquake of similar size or even larger occurring in the same area. This is not GeoNet expressing particular alarm about this specific sequence. It is the standard, honest statement that seismology cannot currently forecast the maximum size of an aftershock sequence in advance, and residents are advised to treat that uncertainty as a standing background condition rather than a specific warning of worse to come. The second, and in the very near term, probably more pressing hazard is not the shaking itself, but what the shaking has done to the ground. The hillsides across this part of the King Country were already saturated from recent heavy rainfall before Saturday's earthquake struck, and strong shaking mechanically weakened slopes that are already compromised by moisture, effectively preloading them for failure even after the ground itself has stopped moving. GeoNet has explicitly warned that landslides may continue occurring in the vicinity of the epicenter in the days following the quake, independent of whether further significant aftershocks occur, simply because the combination of saturated ground and recent shaking leaves slopes in a genuinely more fragile state than they were beforehand. The practical guidance flowing from that warning is straightforward. Anyone noticing fresh cracks in the ground, slumping earth, or any other sign of unstable slope, should stay well clear and report the observation from a safe distance, rather than approaching to investigate. And GeoNet's landslide response team has specifically requested these kinds of observation reports from the public as part of its ongoing hazard assessment. One more piece of context is worth including precisely because it heads off a natural but mistaken assumption. 9 days before Saturday's earthquake, on the 16th of July, a magnitude 6. 3 earthquakes struck near Taunau, at the opposite end of the country, deep in the South Island, roughly 1,000 kilometers from Taumarunui. Given how unusual it is to have 2 earthquakes of this size within such a short window, it would be reasonable to wonder whether they are connected, whether one somehow triggered or foreshadowed the other. GeoNet has addressed this directly and ruled it out. The Taunau earthquake occurred on a completely different plate boundary process, one associated with the Alpine fault system and the different tectonic regime governing the South Island, 1,000 kilometers away from the extensional Taupō Volcanic Zone related setting that produced Saturday's rupture. 2 strong earthquakes within 10 days of each other in a country that sits directly across 2 active plate boundaries and one of the most seismically active regions on the planet is best understood as coincidence rather than as any kind of linked pattern or building sequence. What both events do share, though, is a broader reminder that carries real practical weight. Earthquakes can occur essentially anywhere in New Zealand, not only along the most famous and heavily studied fault lines and communities in areas without an obvious, well-known local hazard. Areas like the King Country around Taumarunui are not somehow exempt from the possibility of a significant shallow rupture arriving with little or no warning. Stepping back to take in the full shape of this event, what makes the Taumarunui earthquake genuinely significant is not really its raw magnitude, which by global standards is a moderate, unremarkable number that occurs somewhere on Earth on a near-weekly basis. What makes it significant is the specific and somewhat unlucky combination of factors that came together at that 1.9 kilometers beneath a corner of the North Island that has no properly mapped active fault and no recent memory of anything this severe. A shallow depth that delivered the shaking directly to the surface rather than softening it across 200 kilometers of rock. A location at the tectonically active but geologically understudied edge of one of the most volcanically significant zones on the planet, close enough to Ruapehu to raise immediate and ultimately unfounded fears of a volcanic connection. A fault that nobody has named, sitting in a part of the country where the seismic hazard model simply did not anticipate a rupture of this size, in the same way the Greendale Fault caught Canterbury by surprise a decade and a half earlier. And a historical record stretching back roughly 100 years that shows nothing else quite like it in the immediate vicinity, making this, by the clearest available measure, the strongest shallow earthquake this specific area has produced in the entire span of modern instrumental seismology. It is also worth thinking for a moment about why more than 23,000 people took the time to file a felt report with GeoNet after this particular earthquake, because that number is itself a form of data, a rough proxy for how far and how strongly this rupture actually reached into people's lives. Felt reports are not a perfectly scientific measurement. They depend on population density, on how many people were awake at 4:51 in the morning, and on how many of those who were shaken out of bed thought to log the experience online in the hours afterward. But as a rough gauge of geographic reach, 23,000 reports, spanning from Auckland in the north down to the top of the South Island, describes an earthquake that was felt across a huge stretch of the country's most populated regions simultaneously, all from a single moderate rupture under a rural district. That reach is a direct consequence of everything already described. The shallow depth sending energy straight up rather than dispersing it through 200 kilometers of rock, and the dampening effect of the Taupō Volcanic Zone redirecting the strongest shaking north and south rather than letting it bleed evenly outward in every direction. Put simply, this earthquake did not just happen to Taumarunui. It happened, in a much fainter but still perceptible way, to a large fraction of the North Island at once, and the felt report numbers are the clearest evidence of that reach. There's also a useful comparison to be drawn with New Zealand's place in the broader geography of global seismicity, because it helps explain why an earthquake of this kind is unsurprising in its general occurrence, even while being locally exceptional. New Zealand sits directly across the boundary between the Pacific Plate and the Australian Plate, a boundary that runs the length of the country and forms part of the wider Pacific Ring of Fire, the horseshoe-shaped belt of subduction zones, fault lines, and volcanoes that circles almost the entire Pacific Ocean and accounts for roughly 90% of the world's earthquakes. Being situated on that boundary is precisely why New Zealand experiences thousands of earthquakes every year, the overwhelming majority of them too small to be felt at all, a much smaller number, large enough to register as a genuine jolt, and, on a scale of years to decades, occasional events large enough to cause real damage. Saturday's magnitude, 5.9, sits comfortably within that second category, a size class that New Zealand's seismic network detects with some regularity across the country as a whole, even though this specific location, this specific depth, and this specific historical rarity for the Taumarunui district make the event locally distinctive rather than routine. Context like this matters because it is easy, especially in the immediate aftermath of a strong and widely felt earthquake, to read unusual significance into an event that is, at the national and global scale, an entirely ordinary expression of the tectonic forces New Zealand lives with permanently. The genuine rarity here is not that an earthquake of this magnitude occurred in New Zealand. It is that one occurred at this shallow depth, in this particular undermapped corner of the King Country, with no known fault attached to it. The scientific story here is still being written. Geologists and seismologists will spend the coming weeks and months refining the aftershock locations, narrowing down which of the two candidate fault planes actually slipped, and potentially, if the evidence holds together, formally naming and mapping a fault that, until the 25th of July 2026, existed only as an anonymous stretch of stressed rock somewhere beneath the King Country. Whether that eventual answer arrives quickly or takes years, as it sometimes does in less heavily monitored parts of a country's tectonic landscape, the immediate lesson for the region, and for New Zealand more broadly, stands regardless of which specific plane ultimately gets the credit for Saturday morning's rupture. The ground under a quiet, sparsely mapped corner of the North Island moved with more force and more directness than it has at any point in living seismic memory, and it did so on a fault line that, as far as anyone currently knows, does not even have a name.